Alrighty, guys, can you hear me? Awesome. Are there any questions before we get started? We only have 2 of you, so if there are any questions, then feel free to shoot. So Alexander, I found a note on nets and the Riemann integral. I'm going to post that on up on the Canvas site. Let me just show you. You had asked me last time. We had a discussion about this last time. So here's a note. It's not by me, but it goes over exactly what we talked about. Why are these needed for Riemann integration? And this is actually a pretty well written note. And what he's getting at is exactly these partitions that we talked about last time. Right, so you take these partitions and you can see they don't nest. And so what do? Well, you take the union of them, and then you'll say that delta 3 is bigger than delta 1 and delta 2 because they're both subsets of it. And then you go ahead and you prove this theorem, which is the main theorem for Riemann integrals. So I'm going to post that. I was looking at the schedule. I'm not sure how much time we're going to have to discuss Riemann integration, but I'm hoping we'll get to it at the end. Aya, do we have any questions? Not yet. Okay, then let's get started. So there were I sent out an email, but let me just write it down here so we all sure we have it. We also have it in the lectures, right? So there are 2 dates. There are 2 exam dates. So the first one is the second midterm. This is December 8th in class, right? And then there's the final. This is on December 22nd. It's in our room from 12 to 3 p.m. Right, and only best 2 tests count. Right, so we have the first midterm and second midterm, and then the final. People move the lowest score, and then the other 2 are the ones that count. Yeah. So this is out of both midterms and final. So the final, this is all material, and the second midterm here, the focus is on the newer material. And any questions on this? Do you know the chapters for the midterm? So where we're at is right. The thing that we did not get tested on the first midterm was these connected sets. So it's going to be something about connected sets. Then the other thing, so there's going to be something on connected set in 3.4, and then we had continuity. Spent a lot of time on continuity and on uniform continuity, right? And now we're working on derivatives. We did not do 4.6. We didn't do, and we're not going to do 5.4. And then we'll see how far we get down here in chapter 6. So I would say at least up until 5.3, but without 4.6. Okay. Any other things? Then let's get back to derivatives. Right, so we're working on derivatives. Right, so we have our function. Our function goes from A into R. This is differentiable. At a point C and A, if f of x minus f of c divided by x minus c, if there's a limit as x goes to c, if this limit exists. And remember what that means. That means that for any sequence inside A such that xn converges to c, we will have that the limit, so we call this one here, this is g prime of c. We'll have that the limit as n goes to infinity of f of xn minus f of c divided by xn minus c, that this limit is exactly g prime of c. Right, so for all sequences that converge to c, you want to have this property. So we saw a few results last time. We saw that last time we saw that if attains a max or a min, if f attains a max or min in an open interval, so in A to B, if it attains a max or a min at a point, say C, so I could write this here more neatly as at a point C, in some open interval, well then f prime of C is 0. And the thing to watch out for a little bit is it's the open interval here, right? So if you always need to check the boundary. You always need to check A and B in addition to these points, f prime of C, in addition to those C's such that this is equal to 0, right? Because what could happen is, so we have your closed interval here, A and B, if you're interested in to find the max, like what could happen here is that even though there is a point in the middle where you have a flat slope, it could be one of these points, right? So if it's one of, so here there'll be 3 points to check, right? It'll be this one here, and then there'll be this one here, and then there'll be this one here. And so the max and the min are going to be found among those 3 points. So you always need to check the boundary as well. And at the boundary, you will not in general have this property. You won't have that it's equal to 0. But you could have that, have something that goes up like that. Right here, there'll be a positive slope. And that's where the max is. So that was one thing we checked. These are often called like this is the first order condition. We also looked at, we also had an example. We're going to see another example today of this phenomenon. That so this was one thing we talked about. The other thing we talked about is that f prime of c can fail to be continuous. It can fail to be continuous. It's always some example with it's always this sine 1 over x is like a top maker, and then the question is, what should you scale? What should you scale it with? This one here is not even continuous, so that is not going to be differentiable. Like all differentiable functions, they are also continuous. So sine x of 1 over x, this is not continuous. So I can put an x here, then that makes it continuous. It's not going to be good enough to be differentiable, because you're going to be having x over x, and then you're stuck with this thing that doesn't have a limit as x goes to 0. But what you can do is you can put a square here, and then a 0 here. So this is when x is positive, and this is when x is 0. And now you're going to get a differentiable function, but the derivative is going to involve I think it's cosine 1 over x, and that won't be continuous. And so the amazing thing is that even though f prime can fail to be continuous, f prime does satisfy. F prime always satisfies the intermediate value property. And so that's kind of surprising that you can have discontinuous functions satisfy that will satisfy this intermediate value function, but this is true. Right, so the intermediate value function is the intermediate value property is that you give me. Right, so what does this mean? Well, normally what it would be is like on a picture, I would have a function. This would be my, say, f prime, and I'm drawing it continuously because I can't, these types of discontinuities that f prime exhibits up here, I can't draw them on a piece of paper. But the intermediate value property is if you take a value here of a, so this, here would be f prime of a, right? And then you take another one over here, that would be your b, and this is f prime of b. And then you give me anything. So for any value in between, for any value in between, I can find a number in here between a and b, such that when I take that, plug it into the derivative, out pops alpha. So even though f prime can fail to be continuous, it does satisfy this property. So you can see from here that so if you're given say g of x, say that this is something which is equal to 0 when x is less than or equal to 0 and is equal to 1 when x is positive. I should probably keep it. Right, if I would do something like this, right, so it's equal to 0, it's equal to 0 out here, and then when you get positive, it's up here. This is your g, and then you could ask, does there exist a function going from r to well r, such that compute the derivative, I'm going to get g. What do you guys think about that? What do you guys think? And why is it a no, Alex? I agree. For me, it's a no as well. But can we give an argument for why? I mean, this is g, right? G is the one that has a jump. F here is the one we're asking for. Can I find a function f such that this is true? But we have examples of functions f which has a derivative that is discontinuous. But can it be this discontinuous? Can I have that type of discontinuity in my function? So what if assume for the sake of contradiction, argue about contradiction. So say such an f exists. How do we get a contradiction? Well, we'll use this theorem that we had, the Debye theorem. And Debye says it shows that f prime must satisfy the intermediate value property. So now we want to get a contradiction. What could we choose what could we choose up here? What kind of an alpha could we choose? So set alpha to be, any ideas on what we should choose for alpha to get a contradiction? Set it to be 1. Can I find an x? 1, 0. I don't like the ones in the zeros. I think we should go for something in between. Set alpha prime to be, say, a half, right? Then you would have that. Then you would have that f prime of, say, -1. This would be g of -1. This would be 0. And then you would have that f prime of, say, 1. This would be equal to g of 1. That would be equal to 1. Right. So alpha equals to a half does belong to the interval f prime of -1 to f prime of 1, right? Because half is between 0 and 1. So the Debye theorem says that there exists a c between the 2 points, -1 and 1, such that a half is equal to f prime of c, which is my g of c. And is that correct? This is impossible, right? Because g is right here, and there is no possibility for it to take the value of half. This is nonsense. G of c is never equal to a half. Right, so we argue about contradiction. We said that indeed, let's pretend that there is such a function. Right, and then we get a contradiction. So then the conclusion is that there does not exist such a function. Does that make sense to you guys? What about the rest of you? Alex is good. We only have a couple of students today, so this is a good time to ask questions if this is not clear to you. Like, this could easily be a question on a midterm or on a final. Here's a crazy function. Can you find a function that has that as its derivative? So the mean value, the intermediate value property says that if I have 2 points in the range, right? So 1 point is going to be bigger than the other one. So if there are 2 points in the range, then if a function satisfies this intermediate value property, then it means that throughout all the points in between these two in the range, they are also reached. Right? So you give me anything in between here, I can always find something in here, such that when I plug it into the function, out pops the value here. That's the intermediate value property. And so if there was a function that had a derivative equal to g, then g here should satisfy the intermediate value property. But you can see g does not. It does not satisfy the intermediate value property. If I take something here between 0 and 1, I take anything, then like a half, I cannot find any, I can't find any point down here on the x-axis. So when I plug it into G, it spits out a half. And that means that this G here, it's not a derivative. Because if it were a derivative, it would have to satisfy that property. Okay. Yeah, is that mostly clear? Is there something here that is still missing? So it's kind of, it's a bit puzzling that you can have functions that are not continuous, but you still satisfy this intermediate value property. But these two things are strictly different. So we've just something about terminology. So if additionally, if prime is continuous, then we say that f is not just differentiable, but it is continuously, I can spell continuously differentiable. And people don't want to write that. You simply just write that f is C1. So that's just terminology. If you impose the additional restriction that not only is f differentiable, but the derivative seen as a function by itself, it's continuous, then we say that f is continuously differentiable, and we write that f is in C1. Okay. But as we've seen, there are lots of functions that are, we've seen lots of functions that are not differentiable. We've seen differentiable functions that are not continuously differentiable, and so on. So today we're gonna try to move forward, and there are a couple of things that I want to prove today. The first one is the mean value theorem. So that's the big topic of this section 5.3, the mean value theorem. So that's our goal for at least the first part of today's lecture. It's going to be to prove this mean value theorem. It goes through a result due to Rolle. And Rolle's theorem says that if I have if I take a function which is differentiable, if it's differentiable, so this is differentiable, and if agrees out at the endpoints. So it's the same out at the endpoints. Well, then what Rolle's theorem says that there exists a point. There exists a point somewhere between A and B, such that at that point, f prime of C is 0. So on a picture, right, there's no mentioning here of continuous differentiable, it's just differentiable. So on a picture, I'll have my interval A to B. Right, and the starting assumption is so if it's differentiable, so it's in particular continuous, there'll be 2 points, this one here, and then this one here. Here, f agrees. This is f of A is equal to f of B. Now, in between, the function moves around, and it gets down to here. What Rolle's theorem says is that somewhere along this interval, there's going to be a point. So when I compute the derivative, I'm flat. And there could be many. It doesn't just, there's also one up here, there's one over here, there's one down here. There could be lots of them, but it says that there's just one. It could be many. That's Rawls' theorem. And given all the prep work that we've been doing, the proof is not that bad. We've done a lot of prep work. So one thing that we have prepped is that A to B, that closed interval up here, this is compact. So so if I look at the supremum over x's in that compact interval, this is a min. This is a max, sorry, this is a max over x's. Right, so there's some point in here. There's some point in here that assumes the max. And likewise, we also have it for the infimum. So all that is good. So let's split it up into two cases. So case one, say that these two things are the same. So now if the min and the max are the same, if the min happens to be equal to the max, well then what can we say about f? If the min is the same as the max, well then what can we say about f? It's a constant. Okay, so if the min is equal to the max, then f is constant. Okay, so then I can just choose, then it's constant on the interval. Right, I just need one point in there that has a derivative that's equal to 0, right? But the derivative of a constant is 0. So any point, so any c works. The harder case is going to be when the min and the max are different, right? So the max is going to be bigger. So let's do that as case two. Case two. So say that the min of f of x in the interval a to b, say that this min here is strictly less than the max. So what can we then say? Well, so can both, so let's write this here as f of it's a min, right? So this is f of say x lower bar, and this here is equal to f of x upper bar. Right, so could we have right, an x bar and x upper bar, they both belong, where x lower bar belongs to the interval a to b, and x upper bar belongs to the interval a to b. So could we have that could we have that x lower bar would be could we have that x lower bar would be say a boundary point A, and x upper bar would be the boundary point B? Is that possible? And why is that not possible, Alex? Yeah, because then f of a equal to f of b will violate this top part here. Very good. Right, that was outstanding. That's where we started out, right? That's where we started out. If we had f of a is equal to f of b, then this would violate the do different, right? And of course, you can swap the roles here. It doesn't have to be that x bar is. You can do them the opposite role. Likewise for a and b swap. So that means that one of the points. So either x bar belongs to a to b, or x over bar belongs to a and b. Open. Whichever one it is, we know from that previous result that the derivative is going to be zero, right? If it attains a max or a min, then the derivative is going to be zero, right? And that's why we've been working on getting it into the interior. So either f prime of x lower bar is equal to zero, or f prime of x upper bar is equal to zero, right? And that was what we were asking for. That's Wallis of Rawls theorem. So if you have a function that agrees out at the two endpoints of your interval, and it's a differentiable function, then somewhere in between, somewhere in that interval, the derivative is going to be equal to zero. Okay, questions on this part? This brings us to the mean value theorem. We already used it, and I gave an application of the mean value theorem for the Lipschitz functions. I'm going to give that application again. So now let's state it and let's prove it. Right, so the mean value theorem, the version we're looking at is called the Lagrange version. So we have a function from a to b, and this is differentiable. This is differentiable. Then what we're saying is that I can find this constant. I can find this constant in between the two endpoints, a to b, such that well, let's look at a picture. So you have your function. This is my function. Here I have my a. Over here I have my b. Right. So what do I do is I connect these two with a straight line. Let's see if I can do this without messing up everything. So if I connect these two, here with a straight line. Right, the slope on this straight line here is, right, I go one out, and what do I go up or down? I'll have my f of a here. Pencil. Uh-oh. So we say f of a here, right, and then f of b is up here. So what's the slope on the red line? I go one out, then I go fb minus fa, and then divided by b minus a. So I'm looking for a constant c somewhere in here. What does that mean? what does the mean value theorem do? Well, it looks for this slope here. I connect the 2 points. Then there is a point somewhere in here such that the slope, find a different color. See if I can do a yellow one here. So I can find a point in here that has that right slope. Right, so the yellow one here is parallel with the red one. Right, and so my point here is that one, C. Right, so they exist as C into A and B, such that this quantity here is exactly f prime of C. Right, and of course this can be rewritten. You can move B and A to the other side. That's all fine. B minus A is not 0. So that's the Lagrange version of the mean value theorem. And the proof here, it's just a little variation of Rawls' theorem. So let me write, what I'm going to do is I'll take f of x. I'll take f of x. I'll just correct it a little bit. What will I correct it with? I will correct it with what I have on the right hand side. So I'll have a minus, and it will be x minus a, and then that slope f of b minus f of a divided by b minus a. I hope I got all this done right. So let me consider this function here. Right, so this is the original function we were given. Oh, it keeps turning off my camera. I don't know. Can you guys? How much of this? Oh. Alrighty, can you see my document camera again? Good. Where were I? So we introduce a new function here, right? So this is the original one. That's the one we started out with. And then this one here is just a linear function. It's an affine function. This is this expression here. This is affine in x, right? So I have a differentiable function. I have an affine function. So this thing here is now going to be this is going to be differentiable as well. So then you apply. So let's see if we can apply Rawls' theorem. What were the two assumptions? Well, one of them was differentiability. Rawls' theorem says that you need differentiability, and then you need the endpoints to line up. Right, so we have differentiability because our original function f was assumed to be differentiable, and this is an affine function, so this is also differentiable. G here is differentiable, so we need to check the endpoints. So to check the endpoints, let's say g of a, what does that equal? Well, g of a equals, it'll be f of a minus, and then you have a 0, so that's that one, and then g of b, well, that's going to be f of b minus, and then you have b minus a times f of b minus f of a divided by b minus a. So what happens is the d will cancel out. I'll get f of b minus f of b plus f of a. Right, so this is good. I have f of a out here. Right, so now I have differentiability, and I have that the endpoints here, they match. So then Rawls' theorem gives me this point somewhere in between, such that g prime of that point is 0, right? Because the endpoints matches up. There's some point in between such that the derivative is equal to 0. And now we just read off what it says up here. What is g prime of c? Well, it's going to be f prime minus, right? And then the derivative with respect to x, this is just going to give me a 1. So it's minus that ratio. And that was what we had to prove, right? G prime is equal to this one evaluated at C. And that's equal to 0. I move this term to the other side, and I get the conclusion that there is such a C, such that the slope of the function agrees with this tangent here. That's the proof of the mean value theorem. Aya is asking what is affine. Right. So a function is linear. A function say f goes from Rd into Rm. This is linear if f of x is equal to say ax, but that's a matrix, right? So this is a coefficient. This will be will it be a d times m? Is that right? I have d rows. Yeah. Right. So in particular, f at 0 is 0. This is a key. This property is always satisfied by a linear function. So an affine function, f going from say Rd into Rm is given by f of x. This is equal to the same linear structure, but then some vector. Right. So again, this one here is a d by m, right, and this one here is a m vector. So here you'll have that f of 0. This is b. So on a picture, linear functions, they look like this. This here is linear, and this here is affine. What does VAT mean?
Sorry, I was just saying that it goes from if it goes from D to M, then the dimension.
I can't follow the last comment. What do you mean by other what?
I was saying it's the other way. Like if it's a function goes from D to M, that the dimensions of A would be M times D, and I guess that would mean that this B would be the dimension of D.
Aya, can you hear me?
Yeah, can you hear me? What?
Aya, can you hear me? I'm not sure. Maybe I'm not sure what WAT is or other what. I'm not trying to ignore you here.
Can you hear me right now, Professor? What? It says that it's working. Am I being trolled?
Oh, okay. But so linear functions, they're the ones that cut through at 0. Affine functions, those are allowed. You move linear functions by just a vector. So just translate them a little bit, and the correct terminology is affine. So there are lots of people who call the top one here linear, but that's not right. Linear functions, you always have the property that d 0 at 0. Okay. So some applications of the mean value, some applications of the the mean value theorem is if I take a function, we had this one in class, right? So if I take a function, you take a function here with f prime bounded, well, then you get Lipschitz. This is Lipschitz. Right, so when we did Lipschitz, it means that the way that you control the values in the codomain, it's very explicit. So to be Lipschitz, you take 2 points in the domain x and y, and you can control their values over in the codomain simply by some big constant times x minus y. Right, so there exists a constant such that this is true. That's what it means to be Lipschitz. Okay, and so how do we do that? Well, so to get m here, we're going to use the mean value theorem. What does it do? It gives us that if f of x minus f of y, right, it gives us that this is equal to some f prime of z. So what I'll do now is I'll move x and y to the other side. This is f prime of z, and then it's x minus y. And then I can take absolute value everywhere. And then I can use that I have this boundedness. So if I write this is less than the supremum over C and R of f prime of C, and then absolute value of x minus y, right? And this here is our m. So we did this argument in class at some point, and I used the mean value theorem. But so now we also proven the mean value theorem, and of course the proof of the mean value theorem has nothing to do with Lipschitz continuity, and so we were able. So now it's rock solid, right? If I have a bounded derivative, then I'm good to go. And one place that this we mentioned now a few times that this f prime, if this f prime here is discontinuous, we need to be like that's a possibility, and so a special case is if f goes from say a to b into R, and if is continuously. So I'm going to add more structure now. It's continuously differentiable. Well, then f is Lipschitz. And the reason is that if I take the supremum over f prime of C, when C runs between A to B, I can use that f prime is continuous, and then I can say that this supremum here, this is bounded. But this relies on that the derivative is continuous and that the interval A to B is compact. Right, so here this here uses one that this is compact, and it uses two that f prime is assumed continuous. Right, so continuously differentiable functions on compact sets, they are uniformly continuous. Are there any questions on this? Aya, did you get your microphone to work, or did the question somehow get clarified along the way? Any questions on any of this? The next thing is about the connection between being differentiable. So this is another application of the mean value theorem, but if we have a function, if I have a function, if f goes from let's say open interval a to b, and then it goes into R, say that it's differentiable. So then the question of, oh, there was a question here. I didn't get the sub part. This one. Yep. So why is this true? Well, recall that if we have this theorem that says that if I have a continuous function on a compact set, continuous functions on the compact sets, D assume like this here is going to be a maximum. Right, there's going to be some C, right? This is going to be equal to f prime of some C hat for some C hat in A to B. Because continuous functions on compact sets, the max and the sub are the same. We proved that. I don't recall how far back that was. We proved that theorem. This was over in the. This has nothing to do with the differentiability. So this was over where we were talking about continuous functions on compact sets. It's this one here. If you take a function that's continuous on a compact set, then there's a max and a min on it. And so the sup and the inf are true max and min. So we had that, I forget how many lectures ago, but we proved this result here. So without the additional assumption that not only is f differentiable, its derivative is continuous, then this wouldn't work. Because I can have, if I don't have continuity, I cannot rely on that theorem. And so in general, f prime here only satisfies the this intermediate value property, and this is not enough. As far as I know, it's not enough. This is not enough to get me this property. So I need to rely on continuous differentiability if I want to get this property here, because I need f prime to be continuous, and then I need well, I'm using that a and b closed interval is compact, and then I'll use that result from a number of weeks ago. Okay, so we want to link monotonicity with differentiability. So take a differentiable function, then the statement is that f is increasing. That f is increasing if and only if f prime of x is positive for all x in the interval a to b. So there's a connection between signing the derivative and then monotonicity properties, right? And if you want to have it to be decreasing, then it's the opposite. And so the proof, say that f is increasing. So I guess I'm going in this direction. Say that f is increasing. Well, so if it's increasing means that if I take x bigger than x0, then that implies that f of x is bigger than or equal to f of x0. Right, so then I'll divide through. Right, so if I move this over on the other side, I'll get that this is positive, right? And then I'll divide by something that is positive. And now take the limit. So this one here will imply that if I take the limit as x goes to x0, so x here is positive, x is bigger than x0, so I'm gonna have to be more indicative to write here that x goes down to x0 of f of x minus f of x0 over x minus x0. Well, this is going to be positive, right? And that's my derivative at x0. So if f is increasing and differentiable, then the derivative is positive. The other way around, this is where we need the intermediate value theorem. This is where we need the intermediate value. This is where we need the mean value theorem. Go from positive derivative to say that f is increasing. So if prime of x is positive, let's see what that gives us. Well, then let me take 2 points. Let me take 2 points, x and y, in the let me take it in the interval a to b. Then what do I know? What do I know? I know the mean value theorem. The mean value theorem will give me something in between. Gives that there exists a z in between, say x to y, such that f of y minus f of x is equal to the derivative times x minus y. Right. So if we keep x is the, which one is x here? X is the, I messed up, right? This is not the right order. I'm dividing by y minus x here. This should be the other way around. It should be y minus x here. Right. I divide by x minus y. I multiply it up on the other side. So here y is the bigger one. So y is the bigger one. Rewrite that too. I take x less than y, x and y in that interval. Right, so what do we have? We have that f prime, it is always positive. So c was somewhere in that interval, so that's good. So this here is positive. Right, that means that f of y is bigger than f of x. Right, that implies that f of y is bigger than f of x. So monotonicity is related to the derivative being positive. And so when I was preparing this lecture, I was reading through the exercises. So let me show you an exercise he has in here. Let me show you an exercise he has in here. So he has an exercise over here where he's discussing this. So he says, from calculus, you know that a differentiable function is increasing if its derivative is positive. Right, and that's what we're seeing here too. But then he says, you got to be a little bit careful about this statement. And so I thought maybe we should be a little bit careful about this statement, and let's try to work through the calculations of this exercise 5.2.10 and see what it comes out to be. So let's try to work through this exercise 5.2.10 here. What is it that one has to be careful about? Let's have a look. If I look at a function, so I have my x, I have 2x squared sine, it's always this sine 1 over x that's going to give us a headache, right? So sine 1 over x, this is when x is, say, between 0 and 1. It's around 0 the action happens, and so we have a 0 here. So this is my function. And we've done this before, but let me just show you how one could try to illustrate it just quickly in Mathematica. So if I look at the function x plus 2 times x squared times sine of 1 over x, if I want to plot that from, say, a value of x up to 1, it looks like this. So if I zoom in on this lower part here, maybe make it a little bit smaller, you can see there are wiggles in here. You can see that it does wiggle, and it wiggles around 0. Right? This is this behavior of sine 1 over x we're seeing. Right? Remember how crazy sine 1 over x is if I don't dampen it by an x factor. If I just plot sine 1 over x, right? It wiggles like crazy. Here it's being dampened quite a bit because I'm multiplying onto x squared. If I just multiply it onto x, it will also get dampened, but not as much as when I multiply it onto x squared. Right, so it's this behavior of 1 over x, this oscillation, this is a troublemaker. And so let's have a look at the differentiability of this function. So this is my f of x. It's continuous because, well, this is continuous, and 2x, this is good enough to kill off the oscillating behavior here, because sine 1 over x is bounded by 1 in absolute value, right? And x squared goes to 0 as x goes to 0. So this here is continuous, and it's also differentiable. We did an example, I think we did this example here in class on Wednesday, but let me just do it one more time. If we look at f of x and it's at 0, the problem is if I subtract away f of 0, then I need to divide by x minus 0. And so what we have here is, what we have downstairs is an x, and what I have upstairs is x plus 2 x squared sine 1 over x. And I factor out the x variable, I get a 1 plus 2x sine 1 over x. And so we have this x times sine 1 over x. And this thing is going to go to 0. If I take absolute value of everything here. And this is going to be bounded by 1 plus 2 absolute value of x. Right, so this term here, that term in here goes to 0, right? So the absolute value of x times sine 1 over x, right? This is bounded by absolute value of x, and this goes to 0 as x goes to 0. So the derivative f prime of x at 0, the derivative is going to be 1. Now outside, we have to take a derivative. We have to compute a derivative of this mess here. So we just quickly do that in Mathematica again. I am interested in computing the derivative of this guy here. So I'll take d and then the expression and then x, and I get this mess here. Let me just copy paste it into my my notes. So this is 1 minus 2 cosine of 1 over x plus 4x sine 1 over x. So what happens now is, so we have a 1 here, and now we have 3 terms up. So we have a 1. This is good. These two look nice, right? And 4x times sine 1 over x, that thing goes to 0 as x goes to 0. The problem maker is this one here. So we have that f prime of 0 is equal to 1, which is definitely positive. But this thing here oscillates like crazy. Right, this term here is basically 0 when x is equal to 0, because 4 times something very small times sine is between -1 and 1. This is basically 0. So we have something that oscillates. It oscillates like 1 minus and then 2 cosine 1 over x. But for x small, f prime oscillates. Can I spell oscillates? And it's going to oscillate between what? This is going to oscillate between -1 and 1. So this is going to oscillate between -2 and what? -2 and 2. And then you have to add a 1. So this is going to oscillate, if you look at the picture, it's this term here. How does this look like when x is close to 0? And you can see, you're starting to see these oscillations, right? You go from, how low can you go? You can go down to -1, I guess. Cosine can go up to 1. So this is that they can go down to -1 and it can go up to 3. So if I look at them on a small interval, you'll see a lot of oscillations. Like that function, it oscillates like crazy between -1 and 3. So even though the derivative at 0 is positive, for x small, the derivative oscillates like crazy in this interval here. But so it's not monotone. Even though the derivative is positive, it's not increasing. So f is not increasing. On say 0 to some epsilon for any epsilon positive. Because as soon as you move a little bit away from 0, f prime oscillates like crazy. And so in the previous result, what we had was stronger, right? We didn't just say that you had to be positive at one point. We said we had to be positive. What was that last sheet? What we said on the previous, one was we were positive here on not just positive at one point, but we're positive at throughout an interval. And then it's true, if you know that the derivative is positive on some interval, well, then the function is going to be increasing on that interval. But if you just know that the derivative is positive at a specific point, it will not give you that the function itself is then going to be increasing on around that point. And this example here it's exactly like that. It's not going to be increasing, even though the derivative is positive. This was all I had. This was all I had prepared for today. Are there any questions about either homework or the lecture today? Are Any comments? That's not the case, then there are and so we won't see each other next week, and there's no homework due next week. I will post the next set of homework, but it won't be due until the week after Thanksgiving. So I'll see you guys in I guess it'll be almost 2 weeks, Monday after Thanksgiving, because we have this change of schedule. So enjoy the Thanksgiving, guys.